So I want to talk about a few problems that have a similar theme, which I call decomposing trees. Essentially, given a tree, we want to decompose the tree into some kind of a path. So the example that triggered this my intention to discuss this type of problem is this problem E from 2020 North American qualifier for ICPC. The problem is called the perfect path control. So this set has 8 problems. This is the third hardest problem. So in general, if you get this problem, you get 6 of them. So the abstraction of the problem is we are given a tree, and every edge has a number, pi, and we want a multi-set of paths so that each edge will appear in exactly pi of this path. So for example, if we look at this example, this edge has a number 1, and it appears in only one path here. And this edge has a number 7, it appears in 1, 2, 3, 4, 5, 6, 7 paths. So of course, it's easy to construct such a multi-set. So in fact, if I make every path a single edge, I just included the appropriate number of times, that will work. But here we want to minimize the number of paths in this multi-set. So we want to find the minimum set of multi-set of multipaths so that all these are exactly satisfied. So for this example problem, this configuration, 10 paths sufficient, 10 paths suffice. So how do we deal with this kind of problem? So in general, if the problem is about the tree, almost always you want to think about it in terms of a rooted tree. So you root the tree, and then you basically use a recursion. So for every node, you look at it and assume that all the children have solved their problems, and then pass you some information. And then you need to solve the problem at your local subtree, and then pass some information to your parent. So essentially, you stare at one node in particular, and then you try to figure out how to what information does it need from the children so that it can solve the problem locally, and then pass this information on to the parent. So yeah, that's the high level technique I would recommend. A lot of this tree problem can be solved by using this high level technique. Essentially, we're doing recursion. So I like to say almost half of the ideas encountered in algorithm are recursion. So here, this is definitely the case where recursion can be very powerful. And another recommendation I have is to get concrete. So oftentimes, if you are having trouble solving the problem by just thinking abstractly, look at the concrete example, look at the test case, and figure out how it works on that. Oftentimes, the insight you gain from solving a small test case will help for solving the problem. So in this case, let's say we root the tree at 0, and then let's look at node 1. So it has 2 children, node 2 and 3. So 2, the edge are to 2. So 2 and 3 are leaf. So there's not much interesting thing to do there. So we have a 5 here, and we have a 3 here, and we have a 3 here to its parent. So because there's a 3 on the edge to its parent, that means there has to be a path, 3 paths that traverse these segment of the edge. Now, since we are trying to minimize the number of these paths, so we want to use each path as much as possible. So then we can extend these 3 in any way we want. So for example, we can, here I guess we extend the path on this figure, extend the 2 to this node and one of them to here. But we can extend all 3 paths to node 2, since it requires 5. So once we extend that, then this edge we only need 2 more to cover this. And if we have a 2 from this child and 3 from this child, then we can connect them to reduce the number of paths. So essentially, when we have a 2 here and 3 here, we are going to need 3 paths. Just to cover this, we're going to need 3 paths. So we're going to have so we're going to need 3 paths. 2 of them will cover both from here to here, and then there's one additional path to cover the remaining one. So essentially, when we get a number of values from its children, and in this particular case, actually the value is nothing more than the value on the edges. So this almost we don't really need to pass something interesting. It's just these numbers. So when we get these numbers, if we have things from our parent, we know this number 3, then we know that can take care of 3 of them. So it's the rest of them we need to take care of. So we need to create the path to cover the rest of them, and we basically try to pair them, right? So we want to pair them so that we can reduce the total number of paths, and we can't really connect the 3 different children. But one path can only connect 2 children. So the most we can do is to pair them. So that basically gives the logic. So given the value from the children, if we take the sum, then we know some of them can be taken care of by extending the path from the parent. So then I don't need to worry about those. The parent node will worry about it. So then whatever number we left, if we divide it by 2 and then we take upper bound, that's the minimum number of paths we need to create that involve this node. But sometimes we actually need more than that. So I guess a good example is let's consider this graph, but rooted at 5. Let's say we actually root the node at 5, and now we'll consider node 4. So node 4, we have 2 children. So one has 2, one has 7, and we have a parent edge has 1. So we know this one can take care of one of them. So then we essentially have 2 and 6. But with 2 and 6, even though if we add them and divide it by 2, we get 4. But 4 paths are not enough because we have 6 here. Only 2 of them can be passed with this. So we actually need 6. So essentially, the number of paths we need is lower bounded either by the sum subtracted by the thing we have in the parent divided by 2, and then take upper bound. Or it also upper bounded by the max I have from a child, subtracting the ones I have from parent. So here, the new path I need to create at node 4 when viewing 5 as a root is bounded by this 7 minus 1. So it's lower bounded by 6. We need at least 6 paths. So I guess let's actually calculate this attempt by thinking about rooting at 5. So 2 and 3, they pass up, they have 5 and 3. So because 3 can take care of these 3 here, between 0 and 1 can take care of 3 here. So what we are left is we need the 3 paths involving 1. So, and then we pass this 3 to 0. Because 3 is less than 7, we don't need to create any paths that that kind of go through 0 and only stay in 0 subtree. We just need to extend a sufficient number of paths between 4 and 0. We extend 3 of them to here, we will cover this 3. So we don't need anything new. And looking at 4, we're going to need 6, as we said earlier. So this, and then we look at 5, we're going to need 1. So we have 3 plus 6 plus 1, that's 10. So that's the logic. Yeah, I think this slide just trying to explain looking at different nodes. So I encourage you, if you want to examine node to figure out how the logic works, I encourage you, one thing is to look at root at 0 and then look at node 1. And the other is you can look at root at 5 and then think about node 4. But one feature that doesn't have in here is the the number of children in here, they're all either 2 or 1, so they don't have more children, which can occur in trees, and we need to take care of. So this is my code for the DFL part, the recursion part. But the overall code is actually just the outer reading data is pretty standard. So I use a global variable to keep track of the answer. So how many new paths are needed for each subtree. And the DFS has the node V and the parent of V, and also I pass in the value on the edge between V and its parent in here, because I need that information to decide how many local are needed. So then I have two sum and the max C. So this is the maximum value from one of the children's, and the sum is and sum is the sum of that value. So I traverse through all the nodes that are adjacent, and then skip the parent, and then I do DFS traverse, and then I add the sum, and I compute the max. So then there's 3 lines to take care of the rest of the logic. One is if the sum from the children is less than or equal to the value on the edge from me to my parent, then I don't need to create anything new. So because whatever path covering the edge from me to the parent can be extended to cover what need to be covered here. So otherwise, I will compute one of the lower bound is the sum minus up the thing that can be taken care of, and then divided by 2 round up. So I do that by +1 divided by 2. So that's one lower bound. And the other lower bound is max C minus up. So if I have the maximum, then even though I can use whatever value to take care of it, the remaining thing, I need at least that many of paths. And it turns out that the new path needed is simply the max of these two, because I can always pair. So long as the maximum is not sort of more than half, there's always ways to pair them. So that's it for this problem. The next example problem I want to discuss is USACO 2020 February. It's in the gold division, the problem called delegation. So we are given a tree of n nodes, and then we want to tell for every value, k value from 1 to n minus 1, determine whether the tree can be partitioned into paths of length exactly k. So as you can see, this is the similarity of these and the previous problem. We are trying to decompose trees into paths. The previous, I guess, not quite decomposed, but we are trying to find paths to satisfy a set of paths to satisfy some condition. But once you get down to the logic of solving the problem, the thinking are fairly similar. The one key is about the matching children's to create the path, because well, given a tree, if the only way to create a path across the node is to connect the two children. So the bound may get slightly, I guess, worrisome, because n is 10 to the 5 and k can be up to 10 to the 5. So nk will be too slow. So how do we get efficient enough? So one observation is we actually don't need to check all the k values. So first, only a k value could possibly work only if k is a divisor of n minus 1, the total number of edges. Because we're dividing the edges into each path of length exactly k, so that's only. And then there's some other things that we can use to prune. So for example, if we cannot divide the tree into paths of length 2, then there's no way we can divide the tree into paths of any even number. Because if we can divide the tree into paths of, say, 6 lengths, then I can cut off each of the 6 lengths into 3 segments of 2. Then I should be able to get a 2. So this observation can be used to prune the search space in 2 ways. So if I find a small k value, it doesn't work, then I know all the multiple k should not work. If I find a big value works, then I know all the divisor of that would also work. So my code doesn't actually use any of those pruning technique. I code only use I will check for every k value that's the divisor of n-1. So it turns out that my code will times out on one of the test case, but it's fast enough for the other 14. So in USACO, I think it's graded based on test cases. So that's I guess that's actually okay. But of course, you can do those pruning, and hopefully they may be able to pass the remaining one. So then the question is, how do we efficiently check for each k value? So this is where it's a tree decomposition. So we basically apply the same method. We root the tree, and then we think about the node in the middle, how to take care of its what do we need from the children, and how to take care of it. So this is a sample test case given in this problem. So the tree has 13 nodes, and I guess the reason is n-1 will be 12. It will have a lot of factors. So make it kind of interesting. So in order to see this, let's say we mentally root the tree at node 8. Let's consider k equals 3. So we want to divide the tree into paths of length 3. So let's see whether we can do it. So let's start from here. So 5, 4. These are not much interesting to do, but when we are at 2, we will have one children tells us, well, here there's a path of length 2, and the 2 other children have a path of length 1. So then what happens is I can match that 2 with 1, create a path of 3. Then I have a 1 left, and this 1 has to be taken care of by the parent. So I basically let my parent know, oh, I have a path 1 here. So because there's also a 1 here, so from parent point of view, there's a path of 2. From node 6 point of view, there's a path of length 2 that need to be taken care of, and the 7 have a path of length 1, so they match. So then the 6 is all happy here, and then 8 have a path 1 here, and then there's a path of length 2 from this branch. So they match, and then there's a path of length 3. So any path of length 3 already taking care of itself. So this is just gone. So we can match 1 and 2, and then that works. So k equals 3 works. Now what about k equals 4? So let's go through the same logic here. So look at node 2. So we have one child have a path 1 and 2, and the path of length 2, and 2 other had path of length of 1 and 1. So that's not going to work, right? Because we can have at most one unresolved path, so that we let the parent take care of. Because I only have one edge to my parent, so that can help me take care of one path that's not length 4. But then the other 2, I need them to add up to 4. If they don't add up, if the length of these do not add up to 4, then I'm going to fail. So just from this node, I can tell I'm going to fail. So then that's basically the logic that we can implement in code. So each node will tell its parent, well, what is the path that I haven't been able to take care of, and what is length? Then the parent will look at all these numbers passed out from the children, and then match them to make a path of k. And if I'm able to, the parent node is able to match everything, and then have at most one resolved, then we are good here. Then we just pass up the length to the parent node. So my code so the DFS part of the code is here. So on 2 slides. So this is a adjacency list for the graph, and then I have a global variable OK. this will be set to true each time before we call DFS on root. And in here, if one node detects a failure condition, it will set this to false. So this is again the node is parent and the value of k is passing here. So again, I use a sum value. So sum of all the value passed out from children because I'm trying to make k here. If the sum is a multiple of k, then I will try to match everything. If the sum is not multiple of k, then I know I should have one pass of that length remaining. I will pass up to the parent to take care of. So that's why the sum is really help me to compute that remainder mod k. And the other value that are passed out by children are stored in this vector. So looping through all neighbors, if it's parent, then ignore. Otherwise, I call the DFS on the children, and then I add 1 because the length of the pass from my child need to add 1 when it goes to me. And because when I call this child DFS, if it fails, it will set OK to false. So for efficiency purpose here, whenever I detect failure, I will simply return 0 because it doesn't really matter what I'm returning at this point. So long as somewhere OK is set to false, then overall we know this has failed. So that's kind of efficiency improvement. And if the value I get from a child is exactly k, this means that from the child point of view, there's a one pass of length k minus 1 that has not been taken care of. But then because that then I add the edge from the child to me, then that's already k. That's already taken care of. I don't need to worry about that part. So I don't consider that. Otherwise, I add that value to the sum, and then I also add that value to the vector. So this is how we use the information obtained from all the children. I first compute the remainder mod k. If it's not 0, then that means there has to be exactly one pass that has that remainder, and I want to get rid of that. And the rest of them has to match up to be length k. So what I'm doing is I find the value in here. If I fail to find it, or if I have an even number of children, that even number of children with the pass that need to be taken care of, then I know I'm going to fail because I need one path to go up, but then the other paths need to be pairwise matched. So if I have even now, after passing this up, I have an odd number, they cannot be matched. So note that anything that can be taken care of length k is already gone. So everything that remains here are less than k. So they have to be paired with something else in order to create the path of length k. So if either of these failure condition is true, I simply set OK to false and then return 0. So there's no point in continue doing. Otherwise, I find the value that need to pass up, so I delete that, and then I sort it, and then I basically do two-pointer checking whether the beginning and end add up to k. So if they don't add up to k, then I will declare failure. If they do, then I will just return the remainder, because this is the part that I didn't take care of and I need the parent node to take care of. So that's it for this problem. So here are a few other problems that are very, very similar. So from the same year USACO, there's a silver problem, clock tree. This actually, I think the silver problem is, in my view, is really no easier than the gold problem. You need to understand modular semantic in order to get that. And then there's a platinum problem. It's similar to this problem. It's a little bit of variation. I think we're trying to determine whether we can decompose the tree into paths of length at least a certain value k. So then when we are doing matching, we don't need the exact. We just, if they're long enough, then we are fine. So but I don't think it's really much harder than the one we talk about, the gold problem. And another problem is Wizard's tour from Code Forces. So this problem is this problem is not a tree. It's actually an arbitrary graph, and I think it's we're basically decomposing the graph into paths of length 2. So we want to do as many of those as possible. But even though it's a graph problem, it's much easier to think about the problem in terms of you do an arbitrary DFS, you create a DFS tree, then every edge will either be a tree edge or a back edge. So then you think about handling from the tree. So that's the right way to think about. So it's still essentially a tree decomposition, except that they have some additional edges that you need to take care of. So that